Welcome to massive open online course on chemical process intensification. So, we are discussing process intensification by membrane under the module 11, and in this lecture we will discuss something more about that membrane engineering in process intensification. In the previous lecture we have discussed the introductory discussion on these membrane processes. Now, in this lecture we will try to discuss more about that how to engineer that membrane to apply different chemical engineering process as per direction of process intensification. So, we know that the crucial challenges in process intensification in chemical engineering process, where we need to have the support of sustainable industrial growth. And in that case there are several possible solution to get that sustainable industrial growth by that offering that process intensification in different aspects. And we have already discussed in our earlier lectures different aspects of process intensification and how that process intensification applied in chemical process systems. And in that case that some design approach to be offered to concrete benefits in the manufacturing and processing and sustainability, shrinking equipment size, boosting plant efficiency, saving energy, reducing capital cost, even increasing safety, minimizing environmental impact, and also maximizing the raw materials explosion. So, under these different categories, that process intensification is actually discussed in our earlier several lectures, also based on different case to case processes of chemical engineering. So, in this lecture I will try to discuss that how the membrane also can be used that for chemical engineering processes for their intensification. Now, we have already discussed that why membrane acts for process intensification. You know that the membrane processes address the goal of process intensification because they have the potential to replace conventional energy intensive techniques, and also this membrane is being used to accomplish the selective and efficient transport of specific components. And also you can say that this membrane can be used to improve the performance of the reactive processes, because we have already discussed that how membrane is being used for hybrid processes of membrane aided distillation processes. There we have also shown several aspects of membrane, how it can be used for reactive distillation in the distillation process. After distillation, how that different components are being separated by the membranes, and based on which that many commercial conventional separation process is going to direct to that membrane separation process, and also it is significant because of its reduction in cost, energy and environmental impact there. And also that this membrane engineering has already provided that interesting solutions to some of the major problems of our modern industrial society. And also we can say that this membrane since they have the potential to replace potential that energy intensive techniques for carrying out different chemical processes, mainly for separation processes, and in that case this is being used to that use for selective and efficient transport of specific components there. And also it is used to improve the performance of reactive processes. Now, of course, this membrane process, whenever you are going to use for process intensification, there should be some competition compared to the other process intensification process. In that case, whether it should be giving the high energy efficiency or not, it may whether it will give you that high separation capacity or not, and also in terms of selective separation, whether it will be suitable or not. whether the capital investment whenever we are considering, then this membrane separation will be competitive or not. So, these things also to be considered whenever the membrane is being used for process intensification for the separation process. Now, what are those that application areas where this process intensification by membrane is possible, and like some example here that the tissue repairing by membrane, pharmaceutical production, food packaging, even production of potable water, even energy generation. These are the in broad area where that membranes can be used as an that potential process intensification device. And in that case, you will see that this membrane can be used for separations which are needed for the manufacture of chemicals, electronics, and ranges of other products based on this different broad area. Now, commercial conventional separation processes in industry are actually converting to membrane separation process, like that in water desalination and also conventional thermal technologies that have been gradually replaced with reverse osmosis there. And in this case, you will see that why membranes are actually being used for process intensification, mainly in the case of that water desalination, even other conventional thermal technologies based membrane separation, and also that reverse osmosis, because in this case the availability of very thin interfaces are actually in the membranes, and the interfaces is basically between different phases for energy and mass transfer, and it represents an important opportunity for the optimization of a wide range of chemical and biochemical operations. So, these are the applications where this commercial conventional separation process in industry are converting to membrane separation processes. Categorically, we can actually assess these membranes for different applications, like that membrane operations are in the several aspects like molecular separation, even chemical transformations, mass and energy transfer between different phases. In the case of molecular separations, in that case you are generally using that microfiltration, ultrafiltration, reverse osmosis based membrane. And in the case of chemical transformations like that membrane reactors, catalytic membranes, membrane bioreactors, etc. And also mass and energy transfer between different phases. In that case, you will see that membrane contactor, membrane distillation, membrane crystallizer, even membrane emulsifiers, membrane strippers, membrane scrubbers, etc. are being used in the area of mass and energy transfer between different phases. Now, out of these various cases where current developments in the field of membrane operations are being carried out, and also their applications in the intensification of chemical manufacturing and processing. So, by using that different aspects of membrane, you will see that several cases of chemical operations are successfully commercialized based on the membrane technologies. Now, such as you can say that desalination process, reverse osmosis, pre and post treatment, even membrane based reactive separations, membrane bioreactor, membrane based hybrid separations, all are actually being different aspects of applications of membrane in different process intensification in chemical engineering processes. Now, if I talk about that desalination process in the membranes, in that case you can see that if you are actually desalination, if you are doing the desalination of seawater through the membrane technology, you will see that this membrane technology, basically that reverse osmosis, which is one of the unique success by membrane technology. And in this case, you will see that it covers around 60% of the total number of worldwide plants, whereas thermal process are representing just 34.8%. Generally, there are two types of where that desalination process, one is thermal and another is membrane, that is reverse osmosis process. So, as compared to that thermal process, this reverse osmosis is having that 60% of the total number of worldwide plants, and there you will see that whereas thermal process representing just 34.8%. That is why the wide application that is based on that membrane process intensification is that in scientific and research communities are gaining day by day interest. And due to its lower energy consumption, high recovery factor and lower cost with the respect to the conventional thermal plants, it is actually nowadays gaining daily there because of several advantages of this reverse osmosis based membrane for the desalination process. Also, in this case it is important to note that this reverse osmosis will allow one of the desalinate waters through a more energy efficient technology with less carbon dioxide discharge from the energy that will be consumed, and also less highly concentrated brine that is to be disposed as a waste. And in that case you will see that the biggest problems in desalination and the primary limitation to widespread application of RO or that inland brackish water desalination, because in this case disposal of less highly concentrated brine is one of the main problem. And for that you have to develop some sustainable process for this desalination process, and that is why this process intensification is coming for that analysis of desalination process by the membrane process membrane technology to solve this problem. And in that case the sustainable and efficient desalination process can be achieved in the future through the integrated membrane system. And in that case main characteristics of the membrane operations are there: great flexibility, operational simplicity and mutual compatibility for the integration of the process. And also in this regard you have to that noted down that membrane processes can be used for RO pre and post treatment instead of conventional technologies, and it offered the possibility of combining different membrane technologies for minimizing the limits of the single membrane units and for increasing the efficiency of the overall system. Now, if you are talking about that reverse osmosis pre-treatment, there are several chemical engineering processes where that stream to go into the main process, sometimes it is required to that treat it by several chemical engineering process like absorption, adsorption and other processes to remove or control that contaminates in the main stream. So, in that case pre-treatment of that stream is sometimes required to separate that inorganic and organic that pollutants for the further operations. So, feed water to reverse osmosis systems needs sometimes pre-treatment to remove inorganic and organic membrane foulants, and also conventional pre-treatment that uses sometimes rotating screens, chemical additives, chemical precipitations and flocculations, that is followed by sand and Curtis filtration. And the process is complex and has a high operating cost. So, that is why this reverse osmosis process is coming just to replace that different that mechanical based separations like rotating screens, chemical additives, all those things. And in that case to remove those micron size particles from its water stream, you have to use that microfiltration or ultrafiltration based membrane, where it gives that alternatives of those screen process like that precipitation process, flocculation or other screening of that chemical additives or removal of chemical additives. And if you are using that RO process, you will see that it will give you the better quality than what are produced by the conventional technology. So, that is why the reverse osmosis based membranes are used for this process intensification based on microfiltration and ultrafiltration to have that intensified way of process. And Membrane treatment systems are also more compact and have lower operating costs than the conventional processes. Like there is a comparison is given in the slides in a table as per Drioli et al. 2011, that a comparison of conventional and microfiltration and ultrafiltration pre-treatment are given here, like some items here: footprint, energy requirements of the pre-treatment, chemical cost, RO capital cost, RO operating cost, RO energy requirements, even RO membrane replacements. So, in terms of those items, how actually these conventional pre-treatment and also microfiltration and ultrafiltration based membrane technology for the pre-treatment of the streams are important. In this case, if you are considering that chemical cost, in that case conventional pre-treatment, it will be high due to the coagulant, disinfection, dechlorination and process chemicals that is needed. Whereas this microfiltration or ultrafiltration pre-treatment, it will require low chemical cost because of the low chemical use there. Also, if you are considering that RO membrane capital cost, in that case conventional pre-treatment process is actually higher than microfiltration or ultrafiltration, since that RO operates at lower flux, and also higher flux is possible in case of microfiltration or ultrafiltration, that results in lower capital cost than conventional pre-treatment. Also, in terms of you are thinking about that energy requirements, conventional pre-treatment generally requires higher cost than microfiltration or that ultrafiltration, due to the high fouling that causes high operating pressures, whereas in microfiltration or ultrafiltrations generally it requires lower operating pressure. And if you are considering that if you replace that RO membrane conventional treatment for that, you can that have high possibility to replace this conventional pre-treatment due to the high fouling, and also that microfiltration and ultrafiltration, in that case this it will be low. And energy requirements, that we told that this less than microfiltration and ultrafiltration, as it could be gravity flow in the conventional treatment, whereas some energy requirements will be higher in the microfiltration or ultrafiltration treatment because of high resistance of the flow through the membrane there. So, that is why you can say that there will be some pros and cons of this ultrafiltration and microfiltration compared to that conventional pre-treatment. Maybe case to case to be handled, where this microfiltration or ultrafiltration may be more useful than conventional pre-treatment. Mainly for industrial scale, sometimes this conventional pre-treatment would be more acceptable than microfiltration and ultrafiltration, whereas for the finer particles to be removed, in that case ultrafiltration should be required, whereas conventional pre-treatment it will not be useful there. So, that is why based on that that criteria of that application that you have to use sometimes this microfiltration or ultrafiltration, which will be giving the more intensification of the process to separate the more finer, even more finer particles. Now, another aspects of that membrane, it is called membrane bioreactor. In this case it is generally combination of the membrane processes like microfiltration or ultrafiltration with a biological wastewater treatment process, and also the activated sludge process. Now, it is also being widely used for municipal and industrial wastewater treatment. And in that case here as shown in figure, that membrane bioreactor as reverse osmosis pre-treatment is also important aspects of process development in this regard. Now, two membrane bioreactor configurations are generally exist. One is called internal or submerged membrane bioreactor, another is called external or side stream membrane bioreactor. You will see that internal submerged bioreactor, it is called it is generally the membranes are immersed in and integral to the biological reactor, and in the case of external or side stream membranes, where you will see that membranes are a separate unit process that is required an intermediate pumping step. So, that is why these two types of membrane bioreactors are important for the process intensification. Here in this shown in the figure, some typical bioreactor mechanism, where you will see that microorganisms and also that other particles, how it will be separated by the membrane to get the clean water, and solids and microorganisms retained by the membrane based on this membrane technology. So, this is why that is the that microorganism separation is called membrane bioreactor. And in this case, what are the basic design principles of this membrane bioreactor, and also what is the treatment process. You will see since this membrane bioreactors combine conventional biological treatment, example activated sludge processes with membrane filtration, which will give you an advanced level of organic and suspended solids removal. In this case, when designed accordingly for this organic compound separations, these systems can also provide an advanced level of nutrient removal, and these membranes have porosities ranging from 0.035 microns to 0.4 microns. That of course depends on the manufacturer. They are actually procured or developed different types of membranes based on their porosities range, and which is generally considered between micro and ultrafiltration. And in this case, to get that optimal operation and secure microorganism separation by that membrane, you have to that develop the membranes in such way that the mixed liquor which is being used should be typically kept in the 1.2% solids range, which is 4 times that of a conventional plant. Now, here one that schematic of conventional activated sludge process in the top, and external side stream membrane bioreactor at the bottom. It is shown based on that Wikipedia in membrane bioreactor. In this case, you will see that wastewater, whatever it is coming to separate there, it should be passed through the grid, and then solid should be removed by pre-treatment by that other mechanical devices, and then pre-treatment will be by reverse osmosis or some other processes, and then aeration process where that you can separate that solid particles by flotations, and then you have to settle it and send filtration and disinfection maybe by ozonation or some other, then effluent will be there. And in case of external side streams, here also the process is given by membrane process. There after separating that aeration zone, that then you have to separate all those very fine particles by this membrane, even also that microorganism by this membrane, instead of conventional process that is used for that microorganism separation by sand filtration or the disinfection process. So, here instead of that disinfection and sand filtration, it is replaced by this membrane to get that effluent after separation. Now, there should be some advantage and disadvantage of those membrane bioreactor whenever it is being used. Of course, that advantage, as an advantage you can say that secondary clarifiers and tertiary filtration process are eliminated. Here we can see here that this one, and also in that case, so the cost will be reduced, and also plant other footprint also will be that optimized. And also it can be designed to prolong sludge age, hence lower sludge production will be there, even high effluent quality, even high loading rate capabilities will be there. As a disadvantage, you can say that high operation and capital cost, membrane complexity will be there, because there will be fouling, there will be clogging of that membrane pores by that solid particles, and also cleaning is a very tough of these membranes to reuse, and also there are capital investment will be more compared to that other conventional process. So, these are the some disadvantages there. Now, if we consider that membrane bioreactor, what are the different factors that affecting the filtration by this membrane bioreactor. If we consider that membrane characteristics are pore size, hydrophilicity, surface roughness, surface change, and other factors, in that case you will see that these are the different factors that may affect on the performance of the membrane bioreactor. And also some other characteristics like sludge characteristics like biomass concentration, aerology, particle size, structure, colloid concentration, and other. So, these are the different factors for sludge characteristics. And also if you are considering the operating conditions, also there will be a certain effect on this membrane performance there, like that biology, what type of biological species are to be separated, and also how that membranes to be actually procured, what are the materials, that also is important. And other operating conditions like temperature, even flux, aeration, and others. So, these are the different factors that you have to remember, that to get that membrane efficiency for particular processes. So, you have to consider these factors, and based on these factors also you can optimize, you can intensify the process by membrane. So, there are several aspects where you can intensify the process. Of course, it is under research that you can intensify the conventional process based on that pore size, hydrophilicity, surface roughness, surface change, and also some other rheological characteristics, colloid concentrations, even other materials based on which these membranes are procured. In that case, this membrane bioreactor also being used for post treatment as well as pre treatment also, and further improvements to the reverse osmosis pre treatment that fall within the domain of process intensification, and that can be achieved through the utilization of nanofiltration for the removal of turbidity, microorganism, hardness, and most multivalent ions. So, this reverse osmosis, when ultrafiltration or nanofiltration membrane being used, in that case you can reduce that that microorganism, but just by reducing the osmotic pressure of the reverse osmosis feed, so that the system can be operated at a higher recovery factors. And that recovery factors of a coupled nanofiltration and reverse osmosis seawater desalination system is that 10 to 12% higher than that of an sewage water reverse osmosis plant based on conventional pre-treatment there. So, it is actually reported by Drioli et al. 1999. They have concluded that the process intensification of this nanofiltration and reverse osmosis hybridization, or you can say that combination of these two may increase the process efficiency up to 10 to 12% higher than that that conventional RO plant. So, that is why that whenever you are intensifying the seawater reverse osmosis process, you have to conjugate that nanofiltration system with that RO process, so that you can get more efficiency of that filtration and also separation process. Now, in case of RO post treatment, in case of desalination process, this brine disposal is one of the main problems that is related to seawater desalination plants. And presently that the majority of the desalination facilities discharge their concentrated waste streams into surface waters or oceans, and this disposal method may damage the environmental unless safe and scrupulous measures are adopted to mitigate and control the impact of the discharge brine. And in that case, membrane engineering for intensification is hence required for this having better efficiency of that separation of brine, or you can say disposal of the brines from that seawater desalination process. Now, in this case, if you are considering that membrane engineering for that intensification of reverse osmosis post treatment, you know that membrane contactor operations may give that better options to solve this issue. In that case, avant grade membrane contactors such as direct contact membrane distillation and membrane crystallization are the two important aspects of membrane process intensification to have this to have that solution of that brine disposal of that desalination of the sea water. And in this case, these two variants of this membrane distillation concept, both of which operate at relatively low temperatures as reported by this Drioli et al. In 1999. Now, since we are talking about the membrane distillation for this process intensification, in that case this membrane distillation is being investigated worldwide, and it is one of the best known methods for process intensification. And membrane distillation that will employs that microporous hydrophobic membranes for separation of aqueous solutions at different temperatures. And also this membrane distillation operation, if you actually use this, an aqueous feed solution is to be brought into contact with one side that is in feed or retentant side of a hydrophobic microporous membrane. And in that case, this hydrophobic nature of that membrane that will prevent the penetration of the aqueous solution into the pores. And also the temperature difference is the main driving force for this process, and therefore, the only volatile components of the feed can be transported through the membrane in the membrane distillation process. And hydrophobicity of that membrane that will prevent that mass transfer of the liquid, whereas a gas liquid interface is created, as shown in figure here in this slides, that how this membrane distillation is being used or is works there in the slides it is shown. Also, traditional unit operations that coupling with the membrane operations is generally provide greater improvements in the efficiency of the overall process, and membrane contactors in water treatment systems can be used for that reduction of the amount of oxygen or carbon dioxide dissolved in the systems in this case, and also removal of harmful components from the polluted waters, and also you can say that diminution of the brine disposal problem that can be solved by these membrane contactors coupling with the traditional unit operations. Now, how it works actually? The temperature gradient on the membrane results in a vapor pressure difference there, and because of that vapor pressures, you will see that volatile components in the supply mix evaporates through the pores, and by diffusion and or convection of the components pass through the compartment of the membrane with high vapor pressures, and also it will be transported to the compartment with low vapor pressures, where they are condensated in the cold liquid or vapor phases. And the manner in which this vapor pressure difference is generated across the membrane is determined by the specific module configurations there. So, what are the different configurations actually are available, like direct contact membrane distillation modules, air gap membrane distillations, vacuum membrane distillations, sweep gas membrane distillations. These are the different kinds of membrane distillation configurations are available. And in case of direct contact membrane distillations, you will see the permeate side consists of a condensation liquid, that is often it is called clean water, that is in direct contact with the membrane. Whereas air gap membrane distillation, in this case the evaporated solvent can be collected on a condensation surface and can be separated from the membrane via air gap. And vacuum membrane distillation, in this case the evaporated solvent can be collected on a condensation surface that can be separated from the membrane via vacuum. And in case of sweep gas membrane distillation, this evaporated solvent can be collected on a condensation surface that can be discharged via cold inert sweep gas instead of just air gap or via vacuum. And in this case some specific advantage also you can get, like lower working temperature and pressure, and thus the lower energy cost and less stringent mechanical properties. And also it will be simple upscaling, simple operations, possibility of higher membrane surface or volume ratios. Even you can get that high sensitive components and high suspended particle content at atmospheric pressure to treat, and also a temperature below the boiling point of the supply that you can do the separation. And typically supply temperature around 30 to 60 degrees centigrade, that will permit reuse of residual heat that will flows, and also the use of alternative energy sources such as sun, wind and geothermics also can be used for this. And supply solution can be separated at a temperature well below the boiling point and under atmospheric pressure. So, these are the several specific advantages that can you can get from membrane bioreactor by this RO treatment. And also the specific disadvantage in this case still form barriers for commercial implementation, because in this case the relatively low permeate flux in comparison with the pressure based membrane processes, flux reductions caused by the concentration, polarization, membrane pollution, water loss due to the conduction through the polymeric membrane, and poor weighting. These are one of the notable the disadvantage. And also high cost of membrane distillation modules, and the high thermal energy consumption is there. The economic costs are determined by membrane distillation configuration. So, whatever cost will be based on that configurations. Maybe that this disadvantage you can optimize based on the configurations design. And you can use this membrane distillation process for the production of distilled water and for concentrating aqueous solutions, and also desalting seawater, and the production of clean water from the brackish water are also important applications that is considered, because non-volatile ionic particles are most completely retained by this membrane distillation. Also it can be applied for the water purification in the pharmaceutical, chemical and textile industries, and for the concentration of fruit juices and milk processing. Applications where high temperature processing cause thermal degradation of the process flow, there also you can apply. Even you can apply for the biomedical applications like removal of water from blood, and also in this case you will see that to separate that harmful waste, and in that case it offers greater potential in the textile industry, where that wastewater is contaminated with the dyes. So, you have to separate those dyes by this membrane distillation process. Now, coupling of the membrane systems is also one of the important aspects of process intensification by membrane engineering. In that case these coupling membrane systems offer new opportunities in design, rationalization and optimization of the water distillation cycles. They are emerging as essential tools for achieving like zero liquid discharge, total raw materials utilization and low energy consumption. And generally this consists with the process intensification strategies of getting that low energy consumptions, even sustainable development. And if you are considering in this regard that membrane based reactive separations, already we have discussed in our earlier lecture that membrane assisted reactive distillation, that is also one important membrane based reactive separations. And in this case this hybrid separation of this membrane aided process is significant because of it gives that that better yield, selectivities via equilibrium shift, better energy management, more compact design, even extension of catalyst lifetime, etc. So, based on this you can have this significant intensification of the process by this membrane. And also large scale application areas of the catalytic membrane reactors also are there, like dehydrogenation, steam reforming, water gas shift, and also selective oxidation reactions are also important applications based on this large scale application of the membrane. And membrane crystallization is also another aspect of using membrane for the process intensification. It is an innovative concept related to the implementation of the membrane technology in crystallization processes. It is important because well controlled nucleation and growth kinetics there, fast crystallization can be possible, and also you can reduce the induction time, and also fine modulation of the level and rate of supersaturation is possible. And in this case the membrane can promote the heterogeneous nucleation, and also polymorphic forms, extension of the membrane crystallization concept to anti-solvent crystallization, and production of co-crystals that can be selected based on this membrane crystallization process. So, these are the several significant, or you can say, advantages of this membrane crystallization process. Whereas this membrane crystallization works basically based on the that contact of phases by means of porous membrane with the distillate side. And in this case hydrophobic low surface tension, you can say that membranes should be used for hydrophilic, that is aqueous crystallizing solutions, while hydrophilic membranes should be used for oleophilic solutions. And in this case you will see the gradient of the vapor pressure between the two subsystems includes the induction of the evaporation of the volatile components from the feed solution, and also migration through the porous membrane, and you can have the finally the recondensation of the distillate side based on this membrane crystallization. And also continuous removal of solvent from the feed solutions in a membrane crystallizer is also there, and also the increased solute concentration thus generating supersaturation as shown in figure in the slides. And there are several aspects of that membrane crystallization, like solvent removal membrane crystallization, like where solvent is removed from the crystallizing solution under a temperature gradient where temperature 1, that is in the site 1 2 would be greater than temperature at the site 2. Whereas solvent or anti-solvent demixing by this membrane crystallization also possible, in which the preferential evaporation of the solvent that induces the increase of the anti-solvent volume fraction, thus reducing solubility. Whereas anti-solvent addition, where an anti-solvent is evaporated into the crystallizing solution in vapor phase from the other side of the membrane. So, according to that Dewey et al., the membrane crystallizer that crystallizing the solution is in direct contact with the membrane surface. Therefore, a solute membrane interaction is likely to occur that depends on the fluid dynamic regime. And also you can say that the effect can be due to the both the structural and also chemical properties of the membrane surface. And Dewey et al. 2012 they have explained the fact in the following way, like firstly you can say that the porous nature of the surface that might supply the topographical heterogeneities, where solute molecules are physically entrapped, leading locally to enhanced that levels of supersaturation. Whereas secondly, you can see that non-specific and reversible chemical interaction between the membrane and the solute that can allow the concentrate and reorient molecules on the surface without loss of mobility. Thus, in this case you can have the facilitation of the effective interaction among them and also get the proper crystallization. Now, you can use this for the application in seawater desalination. In this case, integrated that membrane system that containing membrane crystallization units operating on the brine of nanofiltration and or the reverse osmosis stages to reduce the amount of brine and to recover valuable crystalline materials with the controlled characteristics from seawater desalination installations according to Gioli et al. 2012. So, in this lecture we have discussed lot of things about that membrane applications and their mechanism, how the membrane can be intensified based on that its characteristics, even how it can be conjugated with the other separation process to get that intensification of the overall processes. And also we have discussed that application of that membrane bioreactors and also membrane distillation process based on that hybrid system and also their configurations, how it can be used for the process intensification. So, I would suggest you to go further for these membrane applications in this references and also any other references of membrane separation processes. So, thank you for your kind attention for this lecture today.